We will see now a particular type of relation that is called function. A function from A to B is a relation, like the one that we have defined before from A to B, but one that satisfies these two properties. First, for all elements in A, in the first set, should exist an element in the second set such that A relates to B. If we draw the Venn diagrams in general of a function and we have the elements here of A and the elements of B, what this property is saying about the relation is that all the elements here in this side, all the elements in A should have something to what they relate to. So this relate to that, this relate whatever, but what is saying is that all of them, all the elements should have an arrow of which they are source. All of them should have an arrow that starts there. Now, the second property that should satisfy the relation to be a function is that if A relates to B and A relates to C too, then B have to be equal to C. In other words, A, an element A, cannot relate to two different elements. In terms of the Venn diagrams, if we have an element here, it cannot happen that relates to two different things. So that cannot happen. So the B and the C should be the same. It's not allowed for an element to relate to two different things. That's what this property says. If an element is related to this and to this, then these two things should be equal. This situation is not allowed in functions. Let's see now a concrete example, a particular example. So let's see in this example we have this particular relation F that goes from the set A, that is just x, y, z, to the set B, that is the numbers 1, 2, 3, 4. And is painted here what elements, what pairs are in the relation. So we can see here that x relates to 2, that y relates to 1, and z relates to 2. This is this particular relation that we are going to analyze if it is a function or not. So in order to be a function, should satisfy these two properties. So let's start with the first property. So for all A in A, so we have to check all these elements. For all these elements, should exist one element in the second set such that A relates to B. Is this thing happening for all the elements in A? Well, yes. X relates to something, good. Y relates to something, is good. And Z relates to something, good. So all the elements relate to something in the second set. The second property establishes that if two elements, if the same element relate to two elements, these two elements should be the same. In other words, it's not allowed that an element relate to two different ones. So let's see in this case, X relates only to one element. X relates to 2, only to 2, not to 2, to 3, to 4, no. X relates to 2, so that's fine. It's a unique element that relates to. So let's see this other one, Y. Y relates to 1, good. Y relates to 1, only to 1, not to other elements, so that's fine. And Z relates to 2, so Z relates to 2, fine, only to 2, not to 2 and to 3. So because of that, this relation that we have here is a function, since it does satisfy the two properties. First, that all the elements here have some correspondence in the second one, and then that the output for each input, I mean the one that they relate in the second set, is unique. Let's make some variation in the example. Let's consider this other example now, this other relation. So in this case, the relation between the sets A and B is that X relates to 2 and Z relates to 2. So what do you think? Is the first property satisfied in this case? So we have to check that all the elements here have some corresponding here. Well, that's not happening. So X, it has a corresponding, that's good. Z, it has one corresponding, is good. But Y doesn't have anything to correspond to. So Y does not relate to anything here. So because of that, it's not true that all the elements have some element to which they relate to. So in this case, Y is alone there. So the first property is not satisfied, and so because of that, this function, I mean this relation f, is not a function because it fails already the first property. The second, we don't even need to check it because if it fails any of the properties, it's not going to satisfy both, right? So in order to be a function, it does need to satisfy both properties. Let's see this other example. So that is an example in which the first property is true. You see that we look at the first element, it has something, the Y, the other one has something, and this has something. All of them has some B in the other side that they relate to. So because of that, in this case, the first property is satisfied. Let's look at more carefully now at the second property. The second property says that one particular element cannot relate to two different ones. Well, this is failing in this case. We have that Y relates to 1 and Y relates to 3. You see, relates to two different ones. So if it were a function, these numbers would be the same, 1 and 3, and they are not. So we find a case in which the second property is not satisfied. And so because of that, this one is not going to be a function. Since the second property is not satisfied because we find one element here that fails, that is related to two outputs, one input that have two outputs. That is not allowed in functions. A few words now about the notation. The first set, the set A, is called the domain of the function, and the second set, the set B, is called the codomain of the function. So the set that we said from what to what, the first set then is the domain of the function, and the second set is the codomain. In this case, the domain is a set of the letters X, Y, Z, and the codomain is the set of the numbers 1, 2, 3, 4. One more definition. The range of a function is f of A, which is the set of B in B, I mean the elements in the second set, such that there exists an element in the first set such that the image of that element is B. If we write the sets A and B, what we are saying is that for all the elements B here should exist an element A here such that A relates to B. In other words, the range of the function is the subset of B to which the arrows arrive. In this case, this will be the range of this function because only 1 and 2 are elements that come from something. 3 and 4, they don't have any element in A such that they come from. So the range is contained in the codomain. I mean, the range of the function is contained in the codomain B. Sometimes will be as big as B, but sometimes, like in this case, can be strictly smaller. Let's see some examples. So let's see, we have the set A, that are the letters, and the set B, that are the numbers 1 to 3. So the first example is the relation F, that says that the pairs in this relation are going to be A1, I2, and U1. Okay, so this is our relation. So now we have to decide if it's a function. So in this case, we can see that the first property fails. The first property failed because these elements here are not related to anybody in the second set. Remember that the first property says that all the elements in the first set should relate to something in the second. So we can say that in this case, this thing is not a function. Not even try the second property, since does not satisfy the first one, that cannot be a function. Okay, so let's see this other example. The same sets, but now the pairs in the relations are different. So the ones in this relation are A relates to 1, E relates to 1, I relates to 1, O relates to 1, and U relates to 1. All of them relate to 1 here. Okay, so what do you think? Is this in a function? Well, let's think of the first property. The first property says that all of these things here should be source of some arrow. I mean, should be an arrow that starts at them. In this case, this is correct, right? So this is happening. So the first property, it is satisfied in this example. Let's go for the second property. Remember that the second property says that if the same element is related to two elements, those elements should be the same, which means that one element in the domain cannot be related to more than one element in the codomain. So let's see if this thing is true. Let's check with each element in the domain A. Does A relate to more than one thing? No, just to one, so that's fine. Let's see E. Does E relate to more than one thing? No, relates only to one, so that's fine. What about I? I relates just to one, that's fine. And O relates just to one, it's fine. And U relates just to one. So all the elements we check one by one, and all of them satisfy that the output, the thing that they relate to, is unique. I mean, they don't relate to 2 or 3 things. They relate only to one thing. In this particular case, all of them relate to 1, the number 1. Okay, so because of that, I mean, the second property is satisfied. And so that means that in this case, this relation is a function. I mean, this one that we have painted here, the Venn diagrams, it is a function. Let's see this other relation, the same sets, and the arrows in this case are going to be A goes to 1, A goes to 2, and A goes to 3. Okay, that's it. That's this relation. What do you think? Is it a function? Well, it's clearly no, and in this case, it's not going to satisfy actually any of the properties. So the first one that we check, if all the elements had an arrow that starts at them, well, A is fine. But as soon as we go to this, for instance, that one is not related to anything in the other side. So because of that, the first property fails. And what about the second property? So for the second property, we have to check that for each element, they relate to a unique output here. So that is not true in this case. A relates to 1, but they relate to 2. So it related to 2 different things. And of course to 3, even worse, right? But just because of this, because there are more than one arrow coming from A, so that means that is not satisfy the second property. So this other one is clearly not a function, but in particular it's not a function, and it fails both conditions needed to be a function. Let's come back now to a general function, and we are going to state here several properties that those relations, the ones that are functions, may satisfy. So now we start with an f from a to b that we know that is a function. Now, being a function can have some extra properties. Sometimes functions have these properties, sometimes not. So one of the properties possible is the injective property. A function is injective in case that we have two different elements in the domain, and then the images in the codomain are going to be different too. So that means that if you have one element here and another element that are different, so what have to happen is that they have to come here to different elements too. It cannot be that two different elements go to the same element. Okay, so this is okay for being a function, but it's not okay for being injective. Injective means that if we have different elements in the domain, they have to be sent to different elements in the codomain. Another possible property is the surjective property that says that for all elements in the codomain should exist one element in the domain such that is related to it, meaning that if you have in the codomain any element here should have some A that one comes from, meaning that cannot be some element here alone that no arrow arrived to it. That cannot happen. This situation is okay for a function, but it's not okay for a function that is surjective. So in other words, for being surjective, the range of the function have to be the whole codomain. We shouldn't have any elements in the codomain alone that they don't have any arrow arriving to them. And finally, a function is bijective in case that is injective and surjective. For instance, this example that A goes to 1 and B goes to 2 and C goes to 3. We can see that this, first of all, is a function, satisfy the two conditions to be a function, but this function is also injective, since we can see that all the elements here don't have more than one arrow arriving, so it's injective, and also all the elements in the codomain have something where they come from, so this range coincides with the whole codomain. So this is an example of a bijective function, injective and surjective. Let's check these particular functions. In this case, the set A contains the letters A, B, C, and the set B contains the numbers 0 and 1. And in this first example, this relation says that A relates to 0, and B relates to 0, and B relates to 1, which automatically make this relation to not be a function. This cannot be a function because this is exactly what is forbidden in the second condition of functions. So this one, the first one, is not a function. Then there is no further classification. We cannot say if it's injective, surjective, whatever, because this is just not a function. Let's see this other example. Same set A and B, but in this case, A is related to 1, B is related to 1, and C is related to 1. Well, first of all, this one is a function, since we see that the three things that we have to look here in the domain, all of them have an arrow starting them, so the first condition is good. The second condition is that in the same element we should never have like two arrows here, and that is okay too. So the outputs are always unique. A relates only to 1, to nothing else. B only to 1, to nothing else. C only to one, to nothing else. So because of that, this one is a function. But now, is an injective function? Is a surjective function? Is a bijective function? Let's see what adjective we can associate to the word function here. Well, first of all, it's not injective because this is what failed for the injection. So in order to be injective, all the elements here should arrive just one arrow. And in this case, arrives 3 arrows there. So this one is not injective. And is it surjective? Well, in order to be surjective, the range, the elements to which there are arrows arriving to them, should be the same that the whole codomain. Well, that's not the case. This element is there left over, right? So that shouldn't happen in a surjective function. Surjective means that all the elements here have an element here from what they come from. In this case, 0 fails, and because of that, this function is not surjective. Let's see now the final example of a relation where the sets A and B, I cannot draw them in Venn diagrams since they are infinite sets, are the real numbers. So the notation that you may have seen in calculus, pre-calculus, wherever you study functions. So we represent the real numbers here and the real numbers here. And so this notation, f of x equal x squared, means that for each value x here, you do the square here, and that will be the point of the function. For instance, in the case of f of x equal x squared, you know that this looks like a parabola, so that would be the representation of the function. This one is a function, since for each element in the domain, the image here in the codomain is unique. That's the first condition of function, and all the elements in the x-axis has a square. I'm able to calculate the square of any element. So this is clearly a function. But is this an injective function? Well, we can see, for instance, if we take the number here, let's say 1 and minus 1, they are going to have exactly the same output, right? Because when you do the image of 1 is 1 squared, which is 1, and the image of minus 1 is minus 1 squared, that is also 1. So we find two different inputs that end up in the same output. So that means that this function is not injective. And it's not surjective either, since we see that in the codomain here, this part of the codomain is a range. Is where we see red things around. But in this part here, there is nothing. There is no function there. So there is a big part of the codomain that is not part of the range. So the range is only the positive numbers, and the codomain are all the real numbers. So because of that, this function is not surjective. And of course, it's not bijective, since have to be injective and surjective in order to be bijective. Okay, so that's the function f of x equal x squared. So if we change a little bit, then we have now the function, let's say g, that what it does is to each x associate x cubed in the codomain. So the graph of this function will be something like this and like this. So you can easily check that this relation is a function, that satisfies the two conditions for being a function, and also is injective, since we cannot find two elements as before that have the same output. Here all the elements have different outputs, so this function is injective. And if this function is also going to be surjective, since in this case we see function everywhere, and not only in the positive part, but also in the negative part. So this function is injective and surjective. So as conclusion, this one is a function, and it's also a bijective function, since it is injective and surjective.